In this video, we're going to look at several identities that involve these trigonometric functions that we have been looking at with sine, cosine, tangent, and their reciprocals. The first thing that I want to look at is something called cofunctions. Cofunctions are where you match up some of these trigonometric functions such that for particular angles, they are going to be equal to one another. First thing I want to look at is something called a complementary angle. So a complementary angle to an angle alpha is the angle beta such that when I add them together I get 90 degrees. So alpha plus beta is equal to 90 degrees. So if I've got an angle alpha, the angle that is complementary to that angle alpha is the angle such that when I add it to alpha, I get 90 degrees. So in a similar way, I could say that beta is 90 degrees minus alpha. So the angle that's complementary to alpha is the angle beta, which is 90 minus that angle alpha. It turns out that cofunctions of complementary angles are equal. And I will explain what that means and which functions are cofunctions of each other. Okay, so sine and cosine are cofunctions of one another. What does that mean? Well, go back to what we just said. Cofunctions of complementary angles are equal. So if I have two angles that when I add them together, I get 90 degrees. Because cofunctions of complementary angles are equal, that tells me that for two angles such that when I add them together, I get 90 degrees, then sine of alpha should equal cosine of beta and vice versa. Sine of beta should equal cosine of alpha if alpha and beta equal, when added together, equal 90 degrees. Okay. That means sine and cosine are cofunctions of one another. We saw this in our last video where we looked at 30 and 60 degrees. We found that sine of 30 degrees equal cosine of 60 degrees and sine of 60 degrees equaled cosine of 30 degrees. 30 degrees plus 60 degrees equals 90 degrees, so they are complementary angles, but I found that the sine and cosine of each one equaled one another. So if you go back to our last video, you will see that that is the case. It also works with secant and cosecant. They are also cofunctions. Secant and cosecant are cofunctions. So that means that for two angles, alpha and beta, that add to 90 degrees, we should get that secant of alpha equals cosecant of beta. Again, those two angles add to 90 degrees. And finally, we find that tan and cotan, so tangent and cotangent, they are also cofunctions. So again, taking two angles that add to 90 degrees, I should find that tan of alpha equals cotan of beta. Alpha plus beta equals 90 degrees. These are some very useful identities to keep in the back of your mind whenever you have to simplify some of these expressions that are going to involve these trigonometric functions. Sometimes it will help you to condense some of these expressions down and to simplify them. So do keep these in the back of your mind. Some identities that are used a lot are actually the quotient identities. The first one in particular is used a lot in different types of trigonometric problems. For any angle, we'll call it theta. For an angle theta, it turns out that tan of theta is equal to sine of that angle divided by cosine of that angle. Okay, this works for any angle theta. So make sure that you plug the same theta in for each one. So let's say theta equaled 45 degrees. We said that sine of 45 degrees in our last video was the square root of 2 over 2. And cosine of 45 degrees was also the square root of 2 over 2. So if I do the square root of 2 over 2 divided by the square root of 2 over 2, I'd get 1. Well, that is tan of 45 degrees. So this works for any angle. This was just a quick example. You can go back to our last video and double check this. But this particular quotient identity holds true. In a similar way, if I were to take the reciprocal of this fraction, instead of doing sine divided by cosine, if I did cosine divided by sine, so I've taken the reciprocal, I would get the reciprocal of tan. So I would get that cotangent of an angle is equal to cosine of theta divided by sine of theta for any theta. Okay. Another set of identities that are very useful, again, particularly the first one is used a lot, are called the Pythagorean identities. What do these look like? Well, the first one is used a lot in different problems, as we will see throughout this course. Sine squared of an angle plus cosine squared of an angle equals 1. Okay. When we write sine squared and cosine squared, what I am actually doing here is taking sine of the angle, figuring out what that function value of that angle is, and then I'm squaring that value. Okay. And then I'm finding out what cosine of that angle theta is, and I'm squaring that function value. So figure out sine of the angle and cosine of the angle first, and then you're going to square those values. And it turns out that if you do that and add them together, they equal 1. Okay, so that's what that particular identity means. There are two other identities that we actually get from this first identity. I'll call this 1. The second identity that we have, that's also a Pythagorean identity, is 1 plus tan squared of an angle. So again, this is taking tan of the angle and then squaring that function value, is equal to secant squared of that angle. The way that we get this is by taking our first identity and dividing it by cosine squared. Okay, if I take sine squared theta plus cosine squared theta equals 1, and I divide the entire thing through by cosine squared, I would get sine squared of theta divided by cosine squared theta plus cosine squared theta divided by cosine squared theta is equal to 1 over cosine squared theta. Okay. Remember where I'm just by notation. Sine squared theta is taking sine of theta and squaring it. Cosine squared theta, I'm taking cosine of theta and squaring that. So what I have here is I have sine of theta over cosine theta all squared. This thing here is just tan of theta squared, or tan squared theta. Cosine squared divided by cosine squared is just 1. And then 1 divided by cosine squared theta. Again, cosine squared theta is cosine of theta squared. So this would be secant of theta squared, secant squared theta. So that's where this comes from. Similarly, if instead of dividing by cosine squared theta, if I divide it by sine squared theta, so if I would have taken my first identity here and divided the whole thing through by sine squared theta, I would get my third Pythagorean identity. Okay. Couple quick examples of this. The first one is if I was given sine squared of 40 degrees plus cosine squared of 40 degrees. Okay, I've got sine squared and cosine squared of the same angle, and I'm adding those together, so I know that that must equal 1. Okay. That's my first example. Number 2, let's say that I'm taking cosine of 36 degrees minus sine of 54 degrees. What does this equal? Going back to our cofunctions, I can see that 36 degrees plus 54 degrees equals 90 degrees. So those two angles added together equal 90 degrees, meaning that they're complementary angles. And I know that sine and cosine are cofunctions of each other. So I know, because they are cofunctions, that cosine of 36 degrees must equal sine of 54 degrees, because 36 and 54 add to 90. So I know that cosine of 36 degrees equals sine of 54 degrees. And then I'm going to leave that as sine of 54 degrees. And I get 0. So those two terms actually cancel one another out. Finally, the third example that I'm going to do here is 2 times secant squared of 34 degrees minus 2 tan squared of 34 degrees. Okay. What I'm going to do here is to use one of my Pythagorean identities. I know that I have one of those identities that involves secant squared and tan squared. I'm actually using this particular identity here. Okay. If I have secant squared of theta minus tan squared theta, I know that equals 1. Okay, so I've subtracted tan squared from both sides if I do that. That's what I have here, but I've just multiplied it by 2. So I know here I have 2 multiplied by secant squared of 34 degrees minus tan squared of 34 degrees. Okay. From that identity, I know that secant squared minus tan squared must equal 1. So I get 2 multiplied by 1, which is just 2. The last thing that I want to look at here is word problems. I want to go through a couple word problems that involve some of these trigonometric identities and problems that we have been looking at. In particular, something that I want to look at is angle of elevation and angle of depression. Okay, that's the main word problem that I'm going to go through here. If a person is looking up, the angle that the line of sight makes with their horizontal is called the angle of elevation. So if a person is looking upwards from the horizontal, so a person is looking upwards from the horizontal line of sight, the angle that they are looking up at is called the angle of elevation. Okay. So if this line here is the line of sight, so we're looking upwards from the horizontal, then that theta is called the angle of elevation. Okay, and you can see here that we could make a right triangle out of this with that angle of elevation being next to that horizontal and the line of sight. If a person is looking down at an object, okay, so this is the horizontal that is in a person's eye line, but they are looking downwards, so their line of sight is downwards here, then this angle here is called the angle of depression. There is something called a Z angle, if you've ever looked at right triangles before, which says that if I actually draw this out as like a backwards Z, those two angles actually equal one another. So again, I could draw it out as a right triangle that way, or I could have drawn it out as a right triangle this way, completely up to you. But I do have, when I've got that angle that points downwards, so I end up with what would look like an upside down right triangle, I get that angle of depression. But you can always flip that around using a Z angle, and then those angles do actually equal one another. A quick example that I want to look at that is a word problem. Say that I have a 22-foot ladder and it's leaning against a building and it makes 70-degree angle with the ground. I want to know how far up the building does the ladder touch? Okay, if we draw this out, there's the building, there's the ground, and I have this ladder here. I know that it makes a 70-degree angle with the ground. So this is the ladder, and it makes, that ladder is going to give me a hypotenuse for this triangle of 22 feet. Okay. I know I have a right angle here, and then X is the distance between the floor, between the ground, and where the ladder hits that building. So I want to know the value of X. I want to know how high up this building that the ladder hits. I can go ahead and use SOHCAHTOA in order to do this. So if we go back to what we did in our last video, okay, let's look at what we know and what we don't know. I want to know what the opposite side is to the angle. So I want to know the opposite. I have the hypotenuse and I have the angle. If we look at our SOHCAHTOA, I can see that sine of the angle is equal to opposite divided by hypotenuse. So that particular trigonometric function includes everything that I know and want to know. So I know that sine of 70 degrees is going to equal the opposite side divided by the hypotenuse. So X is going to equal 22 multiplied by sine of 70. Sine of 70 degrees you can put into your calculator. Again, just make sure it is in degree mode, and then you're going to multiply that answer by 22. When you do that, I'm going to take this just to one decimal place. It's going to be 20.7 feet. So that tells me that the ladder hits the building 20.7 feet from the ground.